This is a revision video for P5f, Interference of Waves and Light as a Wave. If you stand on a pier looking at the waterways beneath you, you might notice that they are not all the same height. Some are much higher than others. This is because two or more water waves pass over one another and produce a single wave with a new amplitude. This effect is called interference. Interference causes the reinforcement of some waves. This is called constructive interference, and it builds up the wave. This happens if the crests and the troughs of the two waves line up. It creates a wave with an even greater amplitude. In the case of water waves, this will produce an even taller wave with deeper troughs. If the crests and troughs don't line up completely, then you get a fairly random pattern. Interference can also lead to the cancellation of some waves. This is called destructive interference. It happens if a crest from one wave lines up with the trough from another wave, and they cancel out. If this happens to two water waves, then you get a calm area. This effect happens with all types of waves, not just water waves. Interference happens with sound waves, radio waves, microwaves, and even light waves. When two waves reinforce each other, you get a louder sound, stronger radio or microwave signal, or a brighter area of light. If the waves cancel out, then the reverse happens. You get a darker region, a weaker signal, or a quieter sound. If the cancellation is perfect, it will be silent. To make a stable interference pattern, you need the waves produced by coherent sources. Now, in order for the wave sources to be coherent, they must have the same frequency, they must be in phase, and they must have the same amplitude. Coherent sources for light need to be monochromatic or of a single frequency. To produce an interference pattern, the waves from each source need to travel a different distance. This is the path distance. One wave travels half a wavelength more than the other. This is a path difference of half a wavelength. For constructive interference, you need an even number of half wavelengths. Then that means that every time the waves arrive, there will be the crests and the troughs lined up. So those waves will add together to make this constructive pattern. For destructive interference, you need an odd number of half wavelengths. This means that one of the waves will always be shifted over by half a wavelength. So that means that every time there will be a crest and a trough that are lined up, ready to cancel the wave out. Waves with a whole wavelength difference look like the waves with an even number of half wavelengths, because the whole wavelength is two half wavelengths, so it gives the same pattern as a constructive interference pattern. If we look at this diagram, it shows us two wave sources, and then we have some waves that are travelling from those sources. Path A from source 2 arrives here. At this point, it's travelled half a wavelength more than path B, which has come from source 1. So this is an odd number of half wavelengths, which means it produces destructive interference at this point. Path C from source 1 has travelled one whole wavelength more than path D, or it's travelled two half wavelengths, which is an even number of half wavelengths. So those two waves are producing constructive interference. Type of interference you get at different positions depends on the path difference between the two waves at the point. Okay, so here's an example for you to try. The wavelength of two coherent waves is 1 centimetre. The path difference is measured at 2 points. Point A has a path difference of 2 centimetres. Point B has a path difference of 3.5 centimetres. What type of interference is seen at each point? you stop the video now, you could try and work this out. Okay, so the solution. You know that the wavelength is 1 centimetre, so half a wavelength is 0.5 centimetres. Point A has a path difference of 2 centimetres. This is 4 times 0.5, so that's 4 half wavelengths, or an even number of half wavelengths. So this is constructive interference. Point B has a path difference of 3.5 centimetres. Now 3.5 is 7 times 0.5, so this is an odd number of half wavelengths. This gives us destructive interference at this point. And that concludes the section on interference of waves. So if you've got some time now, you can stop the video and try working through some of these graded questions. Okay, so now we're going to talk about light as a wave. And we're going to start talking about ideas about light and how these have changed. So over time, ideas about the nature of light have changed. We now know that light is an electromagnetic wave, but different theories of light have caused some of the fiercest debates in the history of science. Perhaps the most well-known was between famous English physicist Sir Isaac Newton and the Dutch astronomer Christian Huygens. Newton thought light was a stream of particles. Huygens thought light was a wave. There was good evidence to support both sides of the argument, and there were several other scientists on both sides. Newton stated that the evidence that light travels in straight lines was proof of its particle nature. Waves, like sound and water waves, spread out, but light doesn't. A good example of this is the formation of shadows. Each shadow has a clear edge. If light was a wave, it would spread out or diffract around the obstacle and form a blurry shadow. Newton stated that the shadows formed by a solar eclipse were indisputable proof of that light was a particle. Newton was able to explain both refraction and reflection in terms of particles. Throw a bouncing ball at the ground and it bounces back up at the same angle. Newton used a similar model to explain reflection. Particles of light would bounce off surfaces. However, as more evidence was collected, it became clear that not all phenomena could be explained using the model of light as a particle. Newton was wrong, and the model of light had to be changed. The first key piece of evidence for light as a wave is diffraction. It had appeared that light did not diffract. However, light has such a short wavelength that the gap needed to see this effect has to be very, very small. If a tiny single slit is used, light can be diffracted, spreads out from a narrow beam when it passes through the gap. If 2 slits are used, the light diffracts through both slits and overlaps. This forms an interference pattern. Particles do not form interference patterns. The fact that light does this is the final key piece of evidence that light must be a type of wave. The interference pattern you see with light comes about through the double slit experiment. Light from each slit travels different distances. If the path difference is an even number of wavelengths, it gives a bright patch. If it's an odd number of wavelengths, it gives us a dark patch. All electromagnetic waves can be polarized. Polarization only happens to transverse waves. The polarization of light confirms that light is not only a wave, but a transverse wave. Like all transverse waves, the vibrations are at right angles to the direction of the wave motion. These vibrations might take place in any plane as the wave travels forwards, example, up and down, from side to side. Light from most sources, such as light bulbs or the sun, is not polarized. The vibrations take place in all possible planes. A polarizing filter only lets vibrations pass in one possible plane. So in the diagram, we've got unpolarized light, we've got vibrations in all possible directions. This is unpolarized. If we put a filter in front of that, then what happens is, because the filter is made of these slits running vertically, it only allows the vertical vibrations to pass through. So when we come out on this side, the other side of the filter, you have only got vertically polarised light. And this is called plane polarised light. A filter like this is sometimes called a Polaroid filter. It only lets light through that is polarised in a certain plane. If you have a pair of filters, then you can see that the orientation of the second filter has an effect on what kind of polarisation the light coming through has. In this one we've got two vertical filters, and you can see that the light comes in there, is vertically polarised and is allowed to pass through the second filter, also vertically polarised. Now what will happen if I start to rotate this filter round? Well, if I rotate the second filter, I change the orientation of these slits. So that means that no longer can the vertically polarised light get through. It becomes blocked. So why are these filters useful for us? Well, light is reflected off roads, snow and water. It's only partially plane polarised. Sunglasses that contain Polaroid filter act as a second filter and so block out any of the glare. This can be useful for driving in bright conditions, skiing or water sports. Polarising filters can also be used for cameras to reduce the glare when taking pictures. And that brings an end to the revision section on light as a wave and ideas about light. You can stop the video now if you've got time and work through these graded questions.